How close do I need to have this? Does this work? Does this work?
It works for me.
Okay, it works for you. Does it work for anybody else? Can you hear me? All right, so thanks for having me. I'm David Collins from Florida State University. I'm going to talk about magnetic and density statistics in collapsing MHD clouds. This is work I've done most recently with Blakesley Burkhardt, and Alexei Kritsuk and Paolo Padawan were essential in getting the simulations going, and Wheelie and Mike Norman have also helped out along the way. So we know that some combination of gravity, magnetic fields, and turbulence are central to the star formation process. We know that these are the three dominant processes, so we should understand basically what they look like. So I'm going to talk about some density statistics. I'll talk about PDFs and power spectra. And then I'll talk about some magnetic field statistics, the strength of the field versus Meade field, which is intriguing to me. And then I'll talk about the mass to flux ratio and Zeeman observations. So these are the simulations that I'm going to be talking about. So I basically, for the most part, so we started with a uniform medium and stirred with the magic paddles until we reached the turbulent steady state. And then we let gravity collapse to form our nice high-density structures. So we ran 3 simulations with roughly Mach 10, isothermal ideal MHD, self-gravity. And these are done with AMR MHD to refine the high-density material. These are 5 12-cube simulations with 4 levels of refinement. And they were kind of expensive. Took us about 5 million CPU hours to run. So okay, so here's the parameter space that they kind of live in. So we characterize the simulations in most of the results with the mean beta of 0.2, 2, or 20. Probably a more relevant parameter to characterize the simulations with is the pressure over the RMS field, which is quite a bit lower. So our RMS betas are 0.4, 0.8, and 0.2. Our Mach numbers are about 10. The Alfvén Mach numbers are, again, depending on what you measure, 3 or 1.8, so kind of trans-Alfvénic, 5 or 2 and 9. So this is a pretty super Alfvénic simulation. And our mass to flux ratios are moderately supercritical to largely supercritical. And the virial parameter formally is 1 if you define it as the RMS velocity times the radius over g, which is pretty typical. But if instead you measure the kinetic energy over the gravitational binding energy, you find a value of 10, so which is a result of the fact that the velocity and the density and the potential are all correlated. Okay, so in physical units, we ran for about half a million years. Our length scale is about 4.6 parsecs. With 8192 cubed effective resolution, this gives us a resolution of 116 AU per zone. It's Mach 10. Our mean mass is about 5,000, 6,000 solar masses, and the mean magnetic fields are 13 down to 1.3. And this is what the collapse looks like, because I like to watch clouds move. And you can see the high-density material collapses into this high-density region, which looks long and skinny. And here it is with the AMR, which I like to show because it was expensive both in computational time and drain on my soul in getting the code to work. I'm much older for it. Okay, so what does this look like? So here's what the density PDF looks like. And again, recently this has been a good way to start an argument, but what we find from the simulations is in the solid line we see the initial turbulent gas, which is nicely log normal, and then in the dotted lines we see the self-gravitating gas, which has an excess of material in the weakly magnetized case relative to the other two. We can examine the evolution of the slope of the power law tail as a function of time. So we have alpha is the slope of the power law tail, which ranges from -2 at early times to almost -1 at late times. And this doesn't show much of a tendency to converge or flatten. Additionally, we see a shallower slope, so more material at high density for the more weakly magnetized runs. Additionally, we overplot the spectral slopes and YSO counts for several clouds, 3603, Orion, Auriga, and Maddalena, which have an increasing number of YSO counts, which is intriguing. So the power law index is positively correlated with YSO count as well as core count in the simulations. Density PDF only gives you a little bit of information to get a better feeling on how the material is structured. We wanted to look at density power spectra, and we have a nice analytic theory of what the density power should look like in incompressible turbulence. But what we find with once gravity acts, so this is the power spectra for the 3 field runs, the strong, the mid, and the low field. We find the dotted line is the Kolmogorov spectrum. We find for the black lines are the initial turbulent conditions. We find a shallower spectra than what one would expect for just Kolmogorov turbulence, which is unsurprising because this is Mach 10 turbulence. As time goes on, we find that the power law gets flatter and flatter and flatter until it reaches a positive value. And I should add, this is for the column density power spectra. And here we can see the power spectral slope versus time, and they're largely independent of field strength, but they get substantially steeper than what one would expect for non-self-gravitating runs. These are non-self-gravitating runs with a variety of Mach numbers. It's been demonstrated by us, and Andrei Brezhniak had a paper on this, that these flat, and in our case, rising power spectra are really susceptible to the rare peaks. So one thing we attempted was, could we mimic this behavior by adding a single hot pixel that matches the column density as a function of time. So what we did is took the initial turbulent snapshot and added a single hot pixel that had the value of the peak density for each of our snapshots, and then took the power spectrum of that. And it turns out that we can reproduce, to reasonably good effect, the snapshots that we get from this. So again, this is time increasing in this direction. The thick line is the power spectrum from the initial turbulent case with a single hot pixel, and we can see that we match the basic trend of increasing, and we reasonably approximate the slope. If we're really that sensitive to rare fluctuations, could we possibly remove the effect of these hot pixels, of the rare high column density fluctuations, and return to the state of the background cloud? So can we separate out the effects of gravity and the effects of turbulence in the box? So what we did, so the Fourier transform of a delta function is a constant. So what we did was we took, cut off the top half of the density, the column density map, and took the Fourier transform of that, and just decreased that threshold until the power spectra stopped being flat. So we have the top of our mountain, and then we have the mountain with the mountaintop removed. So in West Virginia, they do this to get the coal. Here I'm doing this to get the turbulence and removing the effects of the self-gravity. So does that work? It works probably better than it should. At the top, we have the high density only. So this is the power spectrum of just the top half above this critical density. And in the bottom half, you see the power spectra for each of our time snapshots, in black is our initial time snapshot. and the other colors are the collapse time steps with the top removed. So this worked better than I expected it to, especially once I thought more about the math. So the next trick is, can we refine this to make sure that these slopes actually match better than they do, and then see if we can do this to actually, in a blinded way, back out what the Mach number of the original cloud was. Okay, so that's what the density is doing. What's the magnetic field doing? So here is the PDF of the magnetic field for our 3 runs. So the low field run in blue, the middle field run in green, and the high field run in red. And what we find is that at high field strength, or there's an excess of high field strength for the more weakly mean magnetized run. So this is the turbulent snapshot where we haven't let gravity act. If we allow gravity to act, we see the same effect to very high field strength. So this is 5 orders of magnitude, 4 orders of magnitude above the mean. And we see a substantially higher amount of high field gas with a more weakly magnetized run. So we can understand this as the mean field influencing the flow. So this is the average cosine of the angle between the field and the velocity. What you expect for random orientation is the gray line. For our strongly magnetized case, at low densities, we have a substantial alignment of the flow with the field, as you expect from a more strongly magnetized simulation. But for the weaker 2 simulations, we get very little. We have very little alignment throughout the entirety of the simulation, which is about what we expect based on what we see with filament alignment for more strongly magnetized runs. In this, the dotted lines show the later times. The solid line is the initial time step, and the dotted lines show the later time step. And this doesn't evolve much in the low-density gas for the early as time goes on, but the high-density gas fluctuates quite wildly for all of the simulations. And we can see, so this is the line of sight magnetic field strength versus column density for the weakly magnetized simulation with the Zeeman measurements in OH and CN. For the initial snapshot, we find that turbulence alone, because we have this shock-driven compression, can reproduce the OH measurements. We need the effect of gravity to show to get the higher density CN points, and this is similar to what Chris had talked about yesterday. So we can reproduce this even with a weak field. Then it's up to making sure we get the rest of the properties to be able to back out what the actual magnetic properties of the gas are. All right, so I have a cloud formation movie with my summary. So thank you.
Perhaps I'm wrong, but to me, supersonic isothermal turbulence sounds like self-contradiction, because what happens in reality if the turbulence is supersonic, then kinetic energy is transformed into heat in shock waves, and then as the temperature increases, the turbulence becomes transonic. It's a self-regulatory system. So how physical is supersonic isothermal turbulence?
The cooling rates are quite high in molecular clouds because they're optically thin. So it's reasonably physical. I think there are measurements in the ISM of log normal density PDFs. But you're right, it's imperfect. So realistically, I should have more physics.
We are going to